Right. Welcome everyone to today's webinar. Today I'll be talking about and providing an introduction to meshing with HELYX. My name is Dan Combest and I'm the manager of ENGYS here in the United States. So some of the goals today that I'd like to accomplish is I want to introduce ENGYS and some of our meshing innovations and learn more about the main features within HELYX, and I'd like you to kind of obtain a sense of how cases are easily meshed within HELYX. And for the sake of time, we'll go ahead and save questions to the very end. Just a little bit about the company. We are global providers of CFD products and services. We were founded in the United Kingdom, so we've just celebrated 10 years of being in business. We've always focused on enabling open source software in industry. And within our organization, we've been open foam developers since 1999. So if you're familiar with open foam, it came out in the 2004-2006 range. And before that, it was a code base called foam. So we have developers within our company that worked on that original code base. So we have lots of experience with this. We currently have 7 offices worldwide. So our home office in the United Kingdom, then we have another office in Germany, Italy, here in the US, Australia, South Africa, and Brazil. And then we have a very experienced, established network of distributors of our software in Japan, South Korea, also here in the US, France, and Spain. Just some information about some of our products. There's 4 main groups. The first one is HELYX. HELYX is a general purpose open source CFD software suite for enterprise. So this is primarily the graphical user interface and the core. And this is what I'll be talking about today. Next, we have Elements, which is an advanced open source CFD software suite for automotive design. This is more of a superset of HELYX. So it has all the features of HELYX, but then it has additional ones that are more specific for automotive design, so external aero, and it really speeds up the setup of those kinds of cases. Next, we have a group called the HELYX add-ons. So within HELYX add-ons, there's an adjoint optimization module. So we have continuous adjoint optimization, and if you're familiar with that, or if you haven't seen that, I did a webinar. I think that was my last one, or the first one that I did in late 2019. Next, we have block-coupled solvers. So these block-coupled solvers are ideal for pump modeling and also compressor modeling. Then we have another specific add-on for marine hydrodynamics, so calm water analysis and seakeeping analysis. Then we have an add-on for advanced multi-phase flow. Finally, we have HELYX OS, which is an open source GUI for standard open foam. More information about this is available on the ENGYS website. So today, what do we want to talk about? We have a variety of people that registered for this webinar. So I wanted to start out with the what, why, how, and when of meshing. So this is a little bit more philosophical about meshing in general, talk about the origins of the mesher within HELYX, do a little F1 demonstration case and just show you the results of that, and then go through the main features and overview of the meshing process, do a demonstration, touch on additional mesh tools that are available within the HELYX GUI, and then leave you with a few take-home messages. So the first one is, why are we meshing? So without diving into CFD in general, the overall gist of it is that we want to simulate physics. And we use these mathematical models to predict physical behavior. So we have these transport equations. So if you're familiar with the first one, this is the incompressible RANS momentum equation, and then the continuity equation. And then also we may want to model species transport. So time-dependent species, advection, diffusion, and a reaction rate for a species. So what we do is we have these model equations, but we need to solve these set of partial differential equations over a defined time and space. That's one single phrase that encompasses a lot of different components of computer science, linear algebra, fluid dynamics. So a lot of that is lumped into these 2 points. So one example is, here's an example from Faurecia, where we wanted to resolve the flow structures and acoustic behavior of a muffler. This was a particularly challenging case because if we're talking about acoustics, then we're talking about very small timescales. If we're talking about pressure waves moving through a domain and resolving these flow features that may cause these acoustic waves, then we need to have a very, large degree of control over how we mesh, how we refine, where we add layers within the domain. So this was a particularly interesting case. So here we've got the inflow of the muffler, and then we've got a few baffles as this fluid moves through this muffler and outputs into this domain. So what are we meshing? Well, we're actually out to create a virtual representation of a system. And I use the term virtual because we're working with computers and we want to be able to model these with computers, so I say virtual representation. Overall, the process is an engineer will define the CAD geometry. So the CAD geometry could be, in this case, be the muffler and also the encompassing domain of the region outside of the muffler where the sound will be traveling. So just the boundaries. From that, we'll create a virtual multi-dimensional domain, multi-spatially dimensional domain of discrete areas and volumes in order to simulate these model equations over. So we've got discrete control volumes that we need to generate using our mesher in which we model all of these equations on. However, there's a caveat to this whole thing, is that, there are resource limitations, and so it requires engineering judgment to do this problem of minimizing the mesh size. So mesh size being the number of individual control volumes. However, we want to maximize potential simulation accuracy. So this takes practice, this takes experience. This is what CFD engineers are good at. So we run enough and we know exactly how to minimize the mesh size. So where the flow features might be in order to capture the physics of importance, or a flow feature of importance. And then we do this in order to maximize potential simulation accuracy. We don't want to have a uniform mesh everywhere that's the same size. We could, but it would be a waste of potential resources. And again, this is the mesh from the previous example right here. Is very center right here would be the muffler. And for this particular mesh, there's several different components. So near the muffler, there's extremely fine cells. Outside of that region, there's a little bit larger cells. Maybe we don't need to necessarily resolve those flow features a little bit more. And then outside of that region, we've got this ever increasing radially extruded mesh from this circular domain in order to capture these pressure waves far from the muffler so we don't get any reflection. Of course, we can have a boundary condition that prevents reflection, but also this extruded domain also helps with that, capturing those pressure waves moving outward from that muffler. So how are we generating a mesh? So we need to be able to generate a mesh to enable resolution of physics. Okay, so steady versus transient. Maybe a mesh would be different for a steady state scenario versus a transient. For transient, maybe, we're using a different turbulence model. Maybe we're using LES or DES, and we need to have different resolution in certain regions to capture flow features that would have been smeared out with a steady state approach. Compressibility. Compressibility is a big thing that we need to think about when we're actually generating a mesh. So is there going to be a shock wave? Where are these shock diamonds coming off the back of this, this nozzle? So we need to be able to refine, either we refine directly on the shock transition itself, or we need to be able to just refine in that region as a whole. There's known and unknown flow features. So if you watched my adjoint optimization webinar, then we had unknown flow features. So we didn't know where that optimal surface was going to grow to. So we meshed the whole domain with a uniform cell size in order to capture every possible flow feature, just in case a surface moved in a direction that we didn't expect. However, if we have this expectation of where these flow features are going to be, we need to have the capability of a mesher to actually put volume refinement, put cells. If we know where a detachment of something's going to happen, we need the capability of being able to add those kinds of features or those cell shapes or those types of components in a mesh in order to capture those physics. Next is complex body motion. So let's say we have a rotating propeller inside, or a rotating wheel, or an impeller, or a pump is moving. That would be complex body motion, and there might be a sliding mesh interface between a stationary mesh component and a sliding mesh component. So we want to be able to capture that and be able to generate a mesh to down the road be able to model those types of physics. And then finally, multiphysics, multi-region. Multiphysics could be species transport. So if we're modeling heterogeneous catalysis, so a species going into a solid catalyst, diffusing into that and reacting on some catalytic site and then coming back out. Or if we've got heat transfer into an electronics board and we've got, or diffusion, or sorry, conduction into like a microchip that's on a motherboard and we want to capture the heat transfer. So we need to be able to generate meshes to be able to solve those kinds of problems. At the same time, our mesh generation approach, we need to be able to mitigate things like limitations in project timescales. That is a big one. So a mesher must be easy to use and actually increase agility. Something can be easy to use, but it just takes a long time to do it. So we need a tool that increases our agility to be able to move back and forth and iterate over different settings within our mesher to be able to go back and forth. And then also, if we're generating these large meshes, if we have a huge amount of, or if we have a moderate amount of compute resources and we want to use large meshes, can we run our mesher in parallel effectively? Next, we need a meshing approach that mitigates the requirements of a solver. Does a solver have a specific format? Does it discretize these transport equations in a specific way, meaning finite element or finite volume, or do we need a way to generate higher order meshes to be able to use a higher order method? Is the solver limited to a structure or unstructured type mesh? Are there limitations in cell shape? So a mesher needs to be able to inherently overcome all of these types of requirements. So when we obtain a good mesh, the mesh size is reasonable. I should have put that in quotation marks, but a more measurable performance indicator of reasonable is that it meets compute resource availability. So if we're generating a 100 billion cell mesh and we don't have the compute resources to do that, then that is an unreasonable mesh size. Oops. And another indicator of a good mesh is that simulations are stable and they scale in parallel. So stable might be related to the quality of the mesh. So the shape of the cells, the volume of the cells, the amount of layers that we might have, and then whether it scales in parallel depends on the solver, but it might be related to the type of decomposition. So we'll split the mesh physically into smaller meshes and solve those on each individual node within our cluster. And another indicator of a good mesh is the important flow features are actually resolved and the physics are predicted over a range of operating points. However, if you're designing a mesh and only one operating point is important, then this particular point isn't necessary. And then finally, results match well with an experimental result. So we can have all of these different things, but if our accuracy compared to an experimental result is poor, then we definitely have room to improve the mesh or even the solvers in physics. So here's just an example. Continuing with the muffler simulation. Again, this is from Faurizia. We have a comparison between the result in HELYX and the experimental result, and we can see that in the teal color right here, this HELYX result, we have very good agreement over a very wide range of decibel levels. So this was partially done with, the success of this was partially from the solver and then also just from a good mesh. So if we had a poor mesh and we didn't resolve the flow features well enough, we wouldn't match any of these points. Okay, so this was a combination of meshing and also with physics. All right, great. We've talked about the what, why, how, and when of meshing. Let's talk about the origins of the mesh within HELYX. And the mesher originated partially from snappyHexMesh. So if you're familiar with snappyHexMesh and OpenFOAM, this was actually, the predecessor was introduced at the OpenFOAM workshop in Milan in 2008 from Eugene de Villiers, and it was developed in part with Eugene de Villiers and Andrew Jackson of ENGYS and Matthias Jensen of OpenCFD. This later became snappyHexMesh. So we have had, deep connection with the origins of snappyHexMesh that's distributed with standard OpenFOAM. However, Andrew Jackson has done a tremendous amount of work over the 10 years that we've been in business, and he's done a great job with continued development to enhance feature capturing and automation, to improve the layer addition algorithm and layer specification method. So now you have more control over the layers to achieve higher layer coverage on different geometries. There's anisotropic volume refinement. Now that kind of feature is within OpenFOAM and within snappyHexMesh, but we've had this for several years now, and users have been able to reduce their mesh count by using anisotropic volume refinement, generation of internal layers on things like boundaries of cell zones or baffles, things like that, topological improvements. There's automatic block mesh creation and decomposition, so you don't even need to really mess with a block mesh dict to create a background mesh in that methodology. There's also improvements in mesh wrapping and small leak closure, so that one is particularly important for, the term would be dirty CAD, so something that might have a gap, and we would need to send that back to an engineer to clean up the CAD before it's sent to the mesher. However, the mesher inside of HELYX is able to wrap those holes if we need to and close these small leaks. There's many other extensions. This is just a short list of some of the continued developments that have happened over the last 10 years with helyxHexMesh. All right, so let me talk a little bit about a demonstration case. I like this one just because it's F1, and I think everyone likes to see race cars, and it's also automotive. So the motivation behind this demonstration case was to compare helyxHexMesh, so the mesher inside of HELYX, with snappyHexMesh, with a focus on performance and quality, and to kind of showcase some of the unique features. This is from a much larger presentation, but this has been carved down to just a few slides in order to save time. So here we've got three different comparisons. We've got two modes of HELYX. So there's a HELYX dualized mesher. Then there's HELYX version 303. So right now we're at HELYX version 3.2.1, which is about to be released in the next few weeks. And then this was compared with snappyHexMesh from 1706. Now, immediately you might say, but wait, we're in 1912. Well, there's really not a lot of changes from 1706 to 1912 in terms of layer addition algorithm. So I still expect this to be very similar. In fact, I ran a external aero case on an SUV comparing snappyHexMesh and helyxHexMesh and had similar performance of layer coverage. So for these particular cases, the layer coverage on a vehicle, if we're looking at detachment of a boundary layer, something like that, layer coverage is very important. So for the dualized mesher, we get 100% layer coverage on this body. For HELYX version 303, we get 98.9% layer coverage. And for snappyHexMesh, we still get a great amount of coverage, which is 96.9. And I'll go into more detail about those specific parts that might be covered on the vehicle. In terms of total number of layer cells for the HELYX dualized mesher, the dualized layer approach, we have about 10 million more cells, more layer cells than we do with snappyHexMesh. And then we have an improvement or an increase in the number of layer cells from HELYX 303, the standard snap layer addition algorithm, to the dualized layer addition algorithm, just from this jump in layer coverage. And again, it increased the total number of cells within the entire domain. So we've got a range of 81 million down to 65 million. So if you look a little bit deeper on each of these individual components, if we're looking at the dualized approach, we'd see 100% on all of these. So let's look more closely at the standard layer addition algorithm within HELYX. We have a range of different components. So we have between 86.3. So I'd categorize that as poor layer coverage. Generally, if you have something that's below 90% with HELYX, then I would say go back and refine or change some of your settings in order to increase that value. So both of these comparisons were done with very similar, identical quality metrics between these meshers. So it is a fair estimate or a fair comparison between these two. So for this type of coverage, we have between 86 and 98.2 for overall layer coverage of 98.9. And then if we look at helyxHexMesh, we have between 27.5 and 93.2 for an overall layer coverage of 96.9%. So we have a very drastic difference in layer coverage. What happens here when we have poor layer coverage? Well, what's going to happen is as these cells were being added, then it decreased the quality of the mesh, so the layer actually collapsed, and you'll see this periodic collapse of layers along an edge of, say, a wing or along a body. And, in general, that will lead to poorer quality results within your CFD simulation. So if we're looking at the dualized approach, so again, this is 8 near wall layers, and there's a symmetry model, there's a symmetry plane within this, this domain. So we can see right here, we see these layers that are wrapping around this foil within the domain. We see great feature snapping to be able to capture these gaps. We see these edges that are captured very well. Here on the far left, we see other things. Other features which are important are distance refinement. So you can see this kind of edge of refinement. It looks like it matches the profile of the vehicle. This is distance-based refinement. And then we see something here that's a little bit more orthogonal and square right there. That is a volumetric refinement, which has been also projected onto the surface boundary of this domain. So we've got distance refinement, we've got feature edge capturing, we've got lots of different things happening within this. So comparing overall performance, this was done on ENGYS's cluster of Intel processors, and this was completed using both HELYX version 303 and then also HELYX version 310. Again, we're on HELYX version 321. So I expect these results to improve even more. We did a scalability study from 48 to 64 to 128 to 256. We kept the number of the number of cores per node to be identical. And, we wanted to keep this core count low so that we weren't hitting things like memory bandwidth problems. So you can see right here, we've got this red line is helyxHexMesh. And so we can see that there is a decrease in overall meshing time as we increase core count. So if we add more cores to this particular case, then it improves its speed. Okay, great. That's what we hope for. And then these other lines down here, we've got HELYX snap layer addition. So the standard layer addition algorithm, we've got really great performance from 48 to 256. Still, this is much better compared to Snappy. If we're looking at the older layer addition algorithm from HELYX, we see still a little bit higher from 3.1, but still it's very good compared to helyxHexMesh. Now, what's important about comparing 303 to 3.1 is that there was a pretty good improvement. So we're constantly developing on the mesher with every release, and it's improving the mesher's performance and features. So when customers make a feature request or they notice a problem, this is something that's a primary focus of ENGYS, is to create a mesher that is usable within industry and is always improving. And then finally, right here, we can see that the dualized mesher from 301, also it scales, it increases its speed when we increase the number of cores. It doesn't quite scale as well with this particular version as helyxHexMesh, but the trade-off is that we are able to obtain 100% layer coverage. So all the time, the extra time is spent in optimizing the cell shape of the layers themselves, and then also the cells above the layer, in order to increase the quality of those cells. And I'll talk about quality here in a second. So overall, we can see that helyxHexMesh does a great job. It performs well in parallel for the tests that we did. And there is improvement between versions of HELYX. And so I expect these numbers to also improve with HELYX version 3.2.1. Okay, next, let's talk about the main features, and I'll give an overview of the meshing process. This is very quick, and then I'll move into a demonstration and we'll talk more about a specific case. All right, great. So the main features of HELYXHexMesh, It's surface detail preservation, so it's necessary for capturing the original geometry. We want to be able to have a mesh boundary that adheres and captures the original CAD geometry as best as possible. Okay, so that's a main feature of this. There's different refinement controls, surface refinement based on feature, and proximity refinement. Proximity would be like how close one surface is to another surface, then it would increase its refinement. Volumetric refinement, there's 3 different modes: inside, outside, and distance-based. Inside would be if I've got an enclosed STL like a box, and I would say everything inside of this box has a certain cell size. And outside would be everything outside of this box has a certain cell size. And then distance-based volumetric refinement would say within X meters from this surface, I would like the cells to be this size. Okay, great. So really, nice control of surface and volumetric refinement. Next, we've got isotropic and anisotropic volume refinement. Isotropic refinement would be when it's split, a cube is split, then it's identical in the X, Y, and Z direction, whereas an isotropic volumetric refinement would be, I would be able to select how much division there is of that cell in the X, Y, and Z direction. And then finally, there's feature line refinement. If you're familiar with Snappy HexMesh, then you know that you need to generate an eMesh file in order to really capture a feature. helyxHexMesh, all of that feature capturing is all implicit. It's automatically done for you. You don't need to extract these feature lines. However, if you want to use an eMesh file and extract these feature lines yourself and then use a distance-based refinement based on that feature line, then that is a perfect use of feature line refinement. And then finally, handling of imperfect geometries. There's different methodologies for surface wrapping, crack detection, single cell gap closure, surface specific wrapping. So if there's holes in the geometry, then there's ways to handle this during the meshing process. Next, we've got boundary layer cell creation. There's a standard layer addition algorithm, then there's a dualized layer addition algorithm for 100% layer coverage. Then we've got cell and face zoning. Why is that important? Well, cell zones are a way for us to select out a certain portion of the mesh in order to add a specific source term to a momentum equation like porous media or MRF, something like that. And then it also gives us the ability to create multi-region meshes to do something like conjugate heat transfer simulation. And then finally, parallel execution, it scales well in HPC. So all of these features, let's think back of the what, when, how, and why. And we want to be able to have a mesher that has the capability to capture the physics within our domain, and we want to be able to do that easily. And so helyxHexMesh has been designed in order to do that. And another component of that, we want to be able to mitigate things like solver-specific mesh format. What's the discretization of the solver? Can the solver work better under specific mesh types? Well, fortunately, the mesher inside of HELYX is a quality-driven mesher. So it's a cut cell mesher, but it's a quality-driven mesher. And so the key quality metrics within the mesher are things like orthogonality, pyramid volume, concavity, face area skewness, determinants, face weights, volume ratios, aspect ratios, TET decomposition. So there's all these different qualities. There's more than I'm even saying here. And all of these are these quality metrics. There's a designated number and measurement for within the mesher that will give us the best possible solution for the solvers within HELYX. So this mesher was designed to run best with the solvers within HELYX. One of the important things about a quality-driven mesher is that meshes that do not meet the quality criteria are scaled back to a previous high-quality state. So this is perfectly important, very important with something like layer addition. So if it inserted a layer, but it squashed a cell above a layer as it's pushing into the domain, and it created a very skewed cell, or the aspect ratio wasn't very good, then it would collapse that layer. And so that oftentimes is why we see layer collapse with the standard layer addition algorithm. Now, the dualized approach doesn't necessarily suffer by that because it will optimize the shape of these cells that might be pushed in or skewed and combines different cells. So we improve that quality through other methods than we do with the standard layer addition algorithm. Okay, so that's an overview of the quality metrics and that the mesher is a quality-driven mesher. So the first step in meshing is we need to provide a base mesh. And so because HELYX is using a cut cell approach, we have a base mesh, and then we can either create it in the GUI or we can import the base mesh. Then we need to import or convert our CAD to a triangulated surface. And once we've imported those triangulated surfaces, then we can manipulate them like scaling them, rotating them around. We can split off different surfaces that might become different boundary conditions. So we have the facility within the GUI in order to manipulate these different surfaces very effectively to generate boundary conditions or cell zones, something like that. So this background mesh, this represents the coarsest cells in the system, and we're going to label this as level 0. All right. Next, we need to do base mesh refinement. So we need to go through and use the triangulated surface, and we need to actually perform refinements of this background mesh in order to capture this near wall physics. Okay, so we need to go through and determine the surface cell intersections, and then we refine. This refinement is based on the user specified numbers. We can do several types of refinements, which I've already referred to: surface refinements, volume refinements, and feature refinements. I'll talk about those controls when I do a demonstration. Now, how do these refinement sizes actually relate to each other? And so I mentioned the word level. And so everything is with reference back to the level 0. So level 0 is this further cell. Then we've got this layer of level 1. Then we've got this layer of level 2. Then we've got this layer of level 3. And then very close to this engine, we've got level 4. Okay, great. How does that relate to the base mesh spacing? So if we take the cube root of that cube, of that cell, so we're imagining that these cells are perfectly orthogonal, they're perfect cubes, then the characteristic length of that cell will be related to the level 0 measure divided by 2 raised to the level, so level n. All right, so this is very simple math that we can actually determine very easily what our level might need to be. So if there's a small feature on this engine that I know the approximate size, and then I say I have to resolve this in my simulation, then it's very easy to calculate what that level needs to be on the surface of that object in order to capture that. All right, perfect. So then we can set our surface refinements on that specific object in order to capture it. If the cell locally is bigger than that geometric component that we want to capture, then it won't snap and refine. It won't capture that small geometric component. So this goes back to the whole, dirty CAD concept. So if we have these small features that we don't really, we could spend time to remove them from our CAD, or if you just use larger cells than what are on the CAD, then you can often just defeature the CAD itself during the meshing process. All right, so you need to be aware of that also while you're meshing. Next, we need to remove the unimportant cells. So the unimportant cells are regions that we're not actually performing our calculation, that we don't care about capturing physics. This is a user-specified material point designated which side of the closed surface to keep. So in that example of an airplane, I want to do an external aero analysis of that wing, then my keep point would be outside of that, the body of that airplane. If I wanted to do some cabin comfort simulations, then I would pick a point inside of the cabin of that, that airplane itself. Next, we would do snapping and smoothing. And snapping and smoothing, so after it removes those cells, we're left with these kind of jagged cubic cells, at the edges of where things have been removed. So we need to snap these points to the boundary themselves to, regain the original surface itself. And this picture right here represents the wing and the engine of the boundary mesh itself that has been snapped back to the the triangulated STL surface. After that, we'll do layer addition. And the standard layer addition algorithm moves in steps. First, it pushes away from the surface, it adds layers, it checks quality, it scales back displacement if there's errors, and then it repeats this process back and forth. For the dualized layer addition, there's other steps in terms of it doesn't necessarily push back on the first step. It will split that first cell using a dualized, it'll calculate the dual of the cell locally, and then it'll start inserting layers. The way that we do this, it ensures 100% layer coverage, and above the cells, above the layer cells themselves, there's some optimization, some changing of the shape of those volume cells, some smoothing of those points and connectivity in order to achieve a really high quality. I'm not going to go through those details right now. However, we do have training that goes through this, and feel free to reach out to support. I have some recordings over some of the details of the theory of this if you're a current customer that I can share. And then finally, it does a rebalance and it writes the mesh to file. And at that point, we can continue and go on with our CFD calculation. All right, so I've talked about the main features and I've gone through the overview of the meshing process. Let's move into the demonstration component. All right, so let me exit out of that and let me open up HELYX GUI. So when you open HELYX, I'm on Windows, I'm on a 2-core machine. When you open up HELYX GUI, you're met with this client-server connection wizard. And so this server connection is a way for us to connect to other remote resources. So right here, I've got my Office workstation. I could also do things like connect to our cluster back in the United Kingdom, or I have a third-party HPC provider that I can connect to their cluster, and I can submit jobs directly from the GUI to their queue from my computer itself. And so it's very powerful to be able to, switch up resources. If you have access to multiple clusters within your company, within your university, within your research group, then you can easily work on something and be able to switch over to a new cluster very easily. For this case, I'm going to choose localhost. So let me let this start. So what happens is it's going to check out a license for the GUI itself. This is a 2-core machine, so we've got a lot going on right now. We've got a webinar, and then we've got this going on, so hopefully everything is good. We're immediately met with cases that I've recently run. If I want to, I can start a new case. Let's just call this cooling, and I'm only going to run on 2 processors. So when I start the GUI, I've got 4 different tabs. I've got meshing, setup, solver, and view. So within meshing, I'm going to do everything related to meshing. Within setup, I'll set up all the physics, boundary conditions. Within solver, we'll launch the calculation and kind of monitor the progress. And then within the view tab, we can actually do post-processing, clipping, streamlines, glyphs, things like that, take pictures. We have different scenes. So today, I'm going to stick within this tab and only talk about meshing. So within all these tabs, we start at the top and we move our way down. So for this case, the meshing algorithm, here's where we select between a dualized or the default layer addition algorithm. I will use default because for this particular case that I've practiced, I've done it with default. Base mesh. So this is the background mesh. Let me set that to a very small number. For the geometry, let me import this geometry from file. So we can import STL, OBJ, ENGYS, and step files. If you import a CAD file, there's an internal triangulation algorithm that will convert your CAD into STL. If you have a great CAD software that you like to use and you're very familiar with converting those to STLs, I say go ahead and use that. All right, let's look at the geometry. For this case, we've got several different geometries. If we're working with something like a scan tire that's gigabytes, I would definitely convert this to a binary format. So we can either use the original format or have it convert internally to a different binary format. I'm going to use the internal. And you'll notice right here that this one's in red. This red means that file may be empty. And the reason why it says that is because for STLs that are very small, maybe there's like 2 or 6 triangles, something that's very small, it'll give a little warning just in case you may have accidentally exported an empty STL. All right, let me hit open. And so right here, if you're familiar with Helix, then you already know that this is tutorial 8, which is one of my favorites because it meshes very quickly on a machine, and then also you can go on and do some very cool things like conjugate heat transfer. All right, so I've got my geometry. Next, I want to go through and try to set the different refinements. So you can see right here, and for each one of these geometry entries, we've got a refinement, zones, and layers. And within refinement, we've got surface refinements and volumetric refinements. So let's look at chip and heat sink. And I've selected both of those by holding down the control key. And let me do 2-2. And so right here, you get a preview of what that local mesh spacing is going to be. And then let's do inlet and outlet also at 2-2. All right, great. For the motherboard and walls, let's leave those as the level 0, but let's add a few layers. So let's go to the layers tab and let's add 3 layers that will stretch at 1.25, a ratio of 1.25 with a final layer thickness ratio of 0.4. There are 5 different criteria for the standard layer addition algorithm that we can set. And so we only need to set 3. We could set the first layer thickness if we had a target Y+ we needed. We could also set the total layer thickness. So we only need to set 3 of these 5 in order to obtain layers. I like to use this combination of number of layers, layer stretching, and final layer thickness. But first cell height is also a great one to use. All right, great. Next, we need to let's create a few cell zones. So you can already see that we're doing a chip and a heat sink. And I already mentioned that we could go on and do a conjugate heat transfer. So let me go to chip and let's go to zones. So let's create an internal type face type. So this will allow us to mark these particular cells as a cell zone in order for us to later on split it off as a different region. All right, so set it to internal. If I was doing something like a sliding mesh interface for modeling a fan, then I would choose boundary or baffle. For this case, let's just do internal. And then for heatsink, let's also do type internal. Let me select this checkbox to create a cell zone, also called heatsink. Next, I need to define a material point. And so this material point, let me move this down a little bit and change the view. All right, so here's the material point. I can either enter it manually, I can grab this point right here, or I can have it recentered in the center of this device. Once I'm ready to go, I can hit create mesh. So in addition to the geometry that I could have imported, I can also use these primitive shapes to do things like create volumetric refinement boxes. If you're clever and you want to create a domain entirely with these primitive objects, in theory you could. And I've done a lot of this. Say you're given a fan blade and you want to create a wedge geometry on one of the single fan blades for this entire experimental domain, you can use all of these different primitive objects very easily. And you'll also notice that these different controls are grayed out. When something is grayed out, it's not accessible at that moment. So right now we're able to import these different surfaces and create a mesh itself, or we could have imported a mesh from another case, or we could have imported a mesh from OpenFoam, from Pointwise, from Fluent. We could also, if we already had a mesh here, let's say we're doing a pump simulation and we have a volute that's already meshed with helyxHexMesh and we want to import the region of the impellers from something like Pointwise or GridPro or ANSYS mesh, we can merge those meshes from a different case. And then also these controls for additional mesh tools are available once we actually have a mesh. So this case takes about a minute to mesh each time we make a change. And if you're watching the progress of this, you can see we're in the layer addition algorithm or layer addition step. If you see lots of zeros, over time, you should see those metrics decrease, which means it's converging and adding layers how we like. So you want to see those move down to 0. Right, doing final load balance. So again, my original points of you need a mesher that enables you to move with agility, to be able to set these things quickly, and then also do things like scale well in parallel. This mesher automatically redistributes and distributes to the number of processors to try to equalize the number of cells on each processor and also minimize the number of faces between. Why would we need to minimize the number of faces between the processors? The lower the number of faces, the smaller the MPI messages are between each one of these processors. Okay, great. So that took a little bit longer than when I tested. However, this is fine. Let's go to mesh and let's see if we can visualize some of the layers. So the number of layers on the surface. Let me hide the surface mesh itself. All right, so we can see a few things. We can see that layers on the motherboard and the box itself are all the way up to the 3 that we designated. And then we didn't designate any layers on the inlet or the outlet patches. So we can see that there's a collapse around the inlet and outlet. So meaning that it decreased from 3 down to 1 very gently. And then also near this, near the chip itself, we see some layer collapse. All right, how do we fix this? That's one thing. We can also look at first cell height. If we wanted to shift, if we wanted a particular first cell height, then we can shift to an approach where we're using first cell height. We can also look at face level meaning what is the local designated level for that particular surface. We can look at those different metrics. Let's go back and let's look at this again. Let's show the surface mesh, right click and go to show. And then one thing that we can also see is that we didn't necessarily capture these inlets and outlets exactly how we wanted. All right, so how do we mitigate that? How do we get around that? All right, so let's go back to chip. Actually, let's go back to inlet and outlet. So let's resolve that first. So what we can do is we can go here and we can check snap surface boundary. So what that does is, because there was no difference in angle as the algorithm moved across this triangulated surface over to these inlets and outlets, there's no difference in the feature angle. So it was a little bit more difficult to just kind of inherently extract those features themselves. So what we can do is we can say snap surface boundary. So it'll snap and get rid of these hanging edges right here. All right, number 1. Number 2, let's also grow layers on the surface of those inlets and outlets. Let's do 3. That way we get rid of that collapse near the inlet and the outlet. In terms of the answer, in terms of a simulation, that doesn't really affect it too much. I just like to do that out of good habit to make nice orthogonal cells at the inlet and outlet. And if we have nice cells where these layers were, and we have kind of this continuity of layers around the entire surface, that's also very helpful. Next, we had some layer collapse around this chip. How do we get rid of that? So we can come in here and we can go to the layers tab for the chip themselves, and we can say enable layer projection. And so what that does is it will, when a layer comes to a point where there's a 90-degree wall with respect to the layer itself, it'll allow the points of the layer to slide up that wall. So by changing that particular setting for the chip, we're going to get these layers that slide up. Let me show you exactly. Let's go to the View tab, and let me take a slice, and let's do a slice through the volume mesh, and let's not decompose the polyhedra. The way that the visualization works is it takes every cell, and if we want, it'll decompose it into tetrahedra. I want to see the actual shape of the cells themselves. So let me hide that. Let's do it in the X direction. Let's see that. And let's do a crinkle cut because I want to see what those cells are shaped like. I don't need to look at that plane anymore. And then let's change the representation. And so here We've got the motherboard layers, and then right here's the interface of the chip itself. And what's happened is it's terminated and then it's picked back up inside of the cell zone where the chip is. What I would like is I'd like these points to slide up the interface of that chip so that we have a nice continuous layers that move throughout this cell zone. So by enabling layer projection, it'll allow those points to slide up so we don't get this layer collapse in that particular point. If I wanted to, if there was a, say, porous media, let's just imagine there was a porous media. Let's go all the way back to meshing. If there was a porous media on the chip and I wanted to do layers on each side of that porous media interface, I could change the number of layers on each side of that cell zone itself. I'm not going to do that because we're not doing porous media right now. All right, great. So chip. We've enabled snapping to get rid of the issue of the inlets and outlets not being resolved as much as we like. We could get around that by also increasing the resolution of the surface refinement, but I don't really want to get away with that because I don't want to add more cells unnecessarily. I'd rather resolve it another way to keep my cell count low. Another thing is we wanted layers to grow on the inlet and outlet, and then we also wanted to prevent layer collapse where these where this chip was having, or where this chip cell zone is. Now, finally, one last thing. Let me go back to view and disable this and come back to the mesh. And let's show all of these. Now, what's going to happen here is, let's see where the inlet is. So we've got an inlet, air is going to come in and it's going to blow over this heat sink, and we might have some flow features behind that. So we may want to add some sort of volumetric refinement. So we've got this volumetric refinement box, which, let's try this. 0.015 to 0.05. Let me change this perspective so we can see this. All right, so we've got a volumetric refinement box behind this to capture any of these things, these flow features that are going to form after shedding off of this device. So I've got a box. Let's call this anisotropic refinement 1. So AR1, let's go to refinements and let's change it to inside anisotropic, and we only want to refine, let's do 2. Let's do AR2. And I only name it with a number in order for me to be able to see it, to identify what that level is without actually clicking on it. All right, I think we're good to go. Let me hit create mesh. One thing you'll notice too is that now that we have a mesh, these other controls kind of came out and became usable. So things like checking the mesh quality or extruding the mesh. One thing that sometimes becomes very necessary. So for example, for this inlet, if I wanted to extrude that inlet so I get some sort of flow profile developed before it enters the system, I could extrude that very easily. Stretch mesh is something where maybe you want to have different aspect ratio cells, so you could collapse the geometry itself. You could mesh on nice orthogonal cells on that geometry, and then you could stretch the entire mesh. This happens sometimes with naval hydrodynamics type simulations. Transform mesh, this is a great one where maybe you'll be meshing on a different length scale and you'll have a mesh on a much larger scale, and then you'll need to convert that overall mesh size to a different scale. Maybe you want to rotate the mesh, scale it, or translate it to move it back to 0, 0, 0, something like that. And then again, if we're doing a conjugate heat transfer case, then we would do split mesh, which if I've got time, I will show you how to do that. Let me let this finish and then we'll move to questions. All right, letting everything finish up. Let me let it reload the mesh. All right, perfect. All right, already we can see some improvements. Let's change our perspective a little bit. Okay, great. So now we're able to resolve these different patches. So because I did the snap surface boundaries, we were able to snap these points to completely regain the geometry of the inlets and outlets. Let me go all the way over here. Ooh, that's very nice. Let's go down and let's look at the surface mesh. Let's check out the layers again. So let's look at number of layers. Let me hide the mesh itself. All right, we've got 3 everywhere. We've got some sliding of that mesh up at the chip itself. I could also have done that for heatsink. Let me make sure that it actually enable. Here's a problem. I forgot to do enable there. However, if I did enable, then it would have slid that up on both sides, which is fine. So we still have some layer collapse right there because of that missing scenario. I could just go back and recheck it and remesh it itself. The important thing is that now we've got layers on our inlets and outlets. Let's go back and let's take a slice and let's see if we can see any of our anisotropic refinements. All right, cool. So here we've got our heatsink and then we've got some anisotropic refinement. How do I know that that's anisotropic? Well, if this was just normal refinement, then these would be cubes. But now we've got a larger aspect ratio because I only did refinement in the Z direction. And we'll see that in the X and the Y, they're both still cubes, still at the level 0 width. So we do this in order to kind of save on our mesh count a little bit. And, anisotropic refinement really comes into play to be able to do that kind of thing. All right, great. So we've got our slice. If we wanted to, we could go on and we could split this mesh into our different regions. I've got cell zones that mark each one of these different regions. Let me just click OK. And let me let it reload. We're doing a little bit of decomposition for the different regions to optimize the decomposition across the processors. And then just like that, now we've got a multiple region mesh. So we've got a chip, we've got our fluid region, which is default, and we've got our heatsink. We can go on and set physics for each one of those, but I will save that for another time. So the additional mesh tools, I briefly touched on these. Within the meshing tab, there's different components for mesh creation, geometry creation, importing, merging, editing the mesh, assessing quality, dealing with multi-region cases, exporting, and then also changing the decomposition. So we've got additional mesh tools within the GUI to kind of keep you very agile moving through this process of meshing rather than just using command line. So just a few take-home messages: physics, budget, kind of resource allocation, solver capabilities all come into play with the selection of a mesher. And HELYX is used in industry and does replace other commercial codes. This mesher was specifically written to run with HELYX. So all of these problems that we've encountered have been particularly addressed within the mesher within HELYX. So HELYX uses a powerful mesher to add layers, do complex refinements, create multi-region meshes, lots of different features. And because we're the ones writing the code and developing this, we can move very quickly when we have a new feature that needs to be incorporated. So HELYX increases meshing agility. So one thing that I'd like to say is talk to us about your CFD wish list. So what kind of physics do you model? Is it cavitation? Here's an example from Raleigh Propeller, which we're looking at cavitation on propellers. And talk to us about what kind of simulations you're doing and what kind of meshing needs there are. Just some closing things. Events. There's the 15th Open Foam Workshop. The abstracts are due by this Friday. The event is held in June, and just is one of the sponsors. I think so far the sponsor of the Open Foam Workshop. So I hope to see you there. Next, we have an upcoming webinar on conjugate heat transfer. Coincidentally, I'm doing conjugate heat transfer mesh today. I will talk about CHT and look at the theory behind it and talk about the setup and go through the CHT solver and talk generally about multiphysics. Also, we've got a blog that we're developing, so blog.engys.com. You'll see things like R&D notes, past webinars, things about continuous adjoint, and then HELYX and elements related content.